Hi, my name is Kevin Taverdi, Assistant Professor in the Department of Chemistry and Biochemistry at the University of Colorado, Colorado Springs, or UCCS. The purpose of this video is to provide students who are currently enrolled in one of my classes that require use of Mathematica with an introduction to this powerful computation and visualization software. Please note that if you have experience using Mathematica or experience writing computer code, some or all of the topics presented here may be below your current ability, so you should feel free to use as much or as little of this tutorial as you want to help you get up and running with this program. It is my hope that students who watch this tutorial will spend less time climbing the steep learning curve of learning a new software program and more time completing interesting calculations in class or on their own and making interesting graphs. So there are many different types of software that are capable of performing the computations and the graphing visualizations required in these courses listed here. I specifically choose to use Mathematica for my courses for a few reasons. First, because it's freely available to all students at UCCS. Second, I think that of all of the software that one could use, Mathematica is one of the more straightforward platforms for students who lack experience in coding. So if this is your first experience in coding, Mathematica is a relatively straightforward program. And third, Mathematica is powerful enough to support both relatively simple calculations that I require in my courses, but as well as more advanced problems in, say, mathematics or engineering or physical chemistry. So it's a tool that students are not likely to outgrow, even if they progress into more advanced coursework or take on a research project that requires customized computational modeling. So this video addresses the 7 topics listed here. I strongly recommend that while students watch this tutorial that they follow along by using Mathematica themselves to perform the same operations that I show. And at times pause the video to explore the functionality for themselves by trying things that I don't explicitly demonstrate. Finally, this tutorial will be performed on a PC that is running Windows 10 with Mathematica version 10.4, although one should be able to follow along well if they are using the same software on a Mac or an earlier version of Mathematica on either a Mac or a PC. With that, we'll jump right into the first topic, which will show students how to obtain Mathematica on their own computers or find a computer on campus at UCCS that has Mathematica on it. Obtaining Mathematica is free for all UCCS students, and if possible, I strongly recommend placing this program on your personal computer, be it either a Windows or a Mac if you're able. To obtain the software, I recommend that you open a web browser like I've done right here, and go ahead and Google University of Colorado software. And what you want is this first hit, this first page, the University of Colorado Boulder software and hardware page. So this is the software and hardware page for the entire CU system, even though it's hosted by Boulder. So you want to click this first link, which is Site Licenses, and then go ahead and scroll down through the software list to Mathematica. So once you click here, it brings you to the Mathematica site license page, and it tells you exactly how to get it. Now notice that there are 2 links here. The first link you will follow and use to download the actual software to put it on your computer, and then you can execute the files which will put Mathematica on your computer. But then to actually be able to use it, you will need to authenticate or activate the software, and to do that you need a key which you will be able to get by following the second link and then using your UCCS credentials to generate that key. So if you are watching this video now on a computer that does not already have Mathematica installed, I recommend that you pause the video and take the time to install it now so that you can follow along with the rest of the tutorial using Mathematica on the computer that you're using and follow each step that I'm doing. So if you do not have access to your own computer, know that Mathematica is part of the standard image loaded onto the computer lab computers across UCCS. So for example, the computers that are located both in the Science Center as well as in the Kramer Family Library all have Mathematica pre-installed on them, so you can just log into one of those computers and use the software. So on this computer, this is my own personal computer, I've already installed Mathematica. So once you've done that, you just need to open the software. And so to do that here in Windows 10, I'm just going to search Windows and type in Mathematica. And what I want to choose is this top option, Desktop App, Wolfram Mathematica 10.4. So just opening this, Mathematica will initialize and open up, and then here I have this central window that indicates Mathematica is running. Now, to actually use Mathematica to help you solve your homework problems or whatever you're trying to do, you need to do some customized coding. Now, a lot of students, when they hear that, they get kind of intimidated, but don't let that scare you, as the coding required to get started within Mathematica is actually pretty straightforward. This coding is done in an environment that is called a notebook. So it's not actually here, you have to open a notebook, and that will be the topic of the next section of this tutorial. So here we are where we left off. Once you have opened this master window in Mathematica, because it's running on your computer, you need to tell Mathematica what you would actually like to compute. The environment that allows you to do that is called a Mathematica Notebook. To open a new notebook, we just choose here, New Document, left click, and choose Notebook. It's always a good idea to start by saving your notebook so that you can come back to your work later if necessary, or if for some reason your computer crashes, you can save your work. Here I will save this notebook on the desktop just by clicking File, Save. I could have hit Control S instead, but I'll do things a long way for this demonstration, and I'll save it on the desktop as Introduction to Mathematica. Note that the extension for this file is .nb. This stands for .notebook. It's a file extension used exclusively by Mathematica. So at this point, it is a good idea to kind of turn our attention to the notebook environment itself. So I'll go ahead and expand this notebook. Note that there are a bunch of toolbars, navigations at the top that have titles like File and Edit and Palettes. We'll go over palettes in topic 4, Typesetting. Below this toolbar is the actual notebook environment itself, at the top of which is this horizontal line, and at the very left edge of this line is a plus sign. So I'm going to start by clicking on that plus sign, and I'm going to choose plain text. So what I've done is essentially created a text cell. Why is it a cell? Well, over on the right hand side, the cell is designated by this vertical divider. So I've designated this cell as a text cell, which means that I can type in it, but no computations are going to be done. And I think it's a good idea to always start with the text cell, because I personally think that it's a good habit to label your Mathematica notebooks with a title that reminds you or later its readers of the purpose. So I'll just title this Getting Started with Mathematica. And then to make it look a little more like a title, I'll highlight it and then right click and choose Style Title. There we go. So I've created one cell, which is a text cell, and it's the title of this Mathematica notebook. So now I actually want to do some computations. That's the purpose of running Mathematica, so I'm going to create a new cell. So to get that line back, I'll click down here, and now I have the option of creating a new cell, but this time instead of choosing plain text, I'm going to choose Wolfram Language Input. So here again, I've created a second cell. Notice that this cell in the very top has kind of a different designation. This has 2 lines, whereas this kind of has a triangle. That's saying that it's a Wolfram Language Input cell instead of a text cell. So now I've made some changes to this notebook. The fact that I've made changes to the notebook and those changes haven't been saved is designated up here by the asterisk after the title to the notebook. So again, it's always good practice to save. So once I save, that asterisk will go away, which tells me that everything that's been changed in the notebook has been saved. So this time, instead of clicking File Save, I'll just on my keyboard hold down Control and push S, and I've saved, and as I said, the asterisk has gone away. So to close this notebook, I will just X out by left-clicking on the X up here in the upper right-hand corner of the notebook. And I'm returned to that main window, which tells me that Mathematica is still running on my computer, but I don't have an environment to do any coding. So if I wanted to return to that notebook, I could either go to my desktop and just double-click on the notebook, or here from the main environment, I could click Open, navigate to my desktop, and then choose Introduction to Mathematica, which is a notebook file, and open it, and then I'm left off in the same place that I was before. And this should be fairly intuitive, as it's the same process as saving and returning to like a Microsoft Word document. So in this topic, we covered opening and saving a Mathematica notebook, which is the environment in which you will do coding, and then how to designate a cell as either a text cell or a Wolfram Language Input cell. In the next section, we'll actually start doing some simple calculations. So here we are again with Mathematica running and our Introduction to Mathematica notebook open. I'm going to place my cursor in the second cell, which we recall has been designated as a Wolfram Language Input cell. And when I left click within that cell, I see there's a flashing cursor on the left hand side, where if I type on my keyboard, those keys will appear in this cell. So I'll start by typing a relatively simple calculation, 2 plus 2, just using my keyboard. Now, because this is a Wolfram Language Input cell, I can now evaluate the cell, which means that Mathematica will start at the very top of the cell and evaluate every line in the cell sequentially, and where appropriate, give an output. So in the cell there is only one line, the 2 plus 2 line, so if I evaluate the cell, I can expect only one output, the result of 2 plus 2 or 4. So let's go ahead and evaluate the cell and see what happens. So to evaluate it, I just place my cursor in the cell and I can choose Evaluation, Evaluate Cells, and you can also see here that there is a keyboard shortcut, Shift plus Enter, which I will use later, but for now I'll just click Evaluate Cells. So the cell has been evaluated. Let's take a closer look at what has happened. So on the right hand side, what was formerly just one cell here has now been split into 2 cells, a top cell, an input cell, and a bottom cell, an output cell, both of which are nested within a larger cell. And then here on the left hand side, we see that our input cell has been given the designation in and then a number, and then the out cell has been given the designation out and that same number. These are both labeled 1 because there is an input-output relationship between these 2 cells, and this has been the first evaluation that has been performed since opening Mathematica on this computer. So, it's important to realize that this is an input-output relationship, and that every time you perform a new input, a new output with a new number is designated. So say that you realized you made a mistake here, and instead of calculating 2 plus 2, you wanted to calculate, say, 2 plus 4. So what you could do is just make a new Mathematica Wolfram Language Input cell, and instead of calculating 2 plus 2, do the same thing that we just did, only with 2 plus 4. But since we realized we made a mistake, we might as well make a change to our mistakenly formatted cell. So I'll just place my cursor here, and on my keyboard, push backspace, and instead of 2 plus 2, I'll type in 2 plus 4. Now notice that since we made a change to the input cell, the input designation has gone away. Likewise, the output cell has turned from black to gray. That's because there's no longer an input-output relationship between these two cells because we've made some change to the input cell. So now let's reevaluate this, and this time I'll evaluate by holding down Shift and pushing Enter on my keyboard. And as we expect, the evaluation changes from 4 to 6. So as a final demonstration of this topic, I'm going to perform an evaluation that doesn't just use one line but uses multiple lines. So I'm going to go ahead and open a new cell, but this time instead of clicking the plus sign and choosing Wolfram Language Input, I'm going to show you a shortcut. So as long as this horizontal line is flashing here, this is where the cursor is, all I have to do is push the enter button on my keyboard, and automatically a Wolfram Language Input cell will be generated. That's the default cell generation when you push enter, so that's convenient. So I'll start by typing in something familiar on the first line, 2 plus 2. Now let's say that I wanted to use the result of this first line, which is 4, later on to compute something else. Now I fully realize that 2 plus 2 equals 4, and that's simple enough to remember, and I could just fill it in later, but for the purpose of this demonstration, just follow along. So because I want to use this result later, 2 plus 2, I will give it a symbolic definition so I don't have to remember it. So specifically, I'll give it the most common symbolic definition of x. So I'm just going to use my arrow key or my cursor to place my cursor over here on the left-hand side of this first line and type in on my keyboard x equals. Now note that x is blue here. That's because it remains a symbol that hasn't been defined yet. So now I'm going to use that symbol in another line of calculation. So I'll place my cursor at the end of this first line and push the enter button, which gives me another line simply by expanding the vertical length of this cell. So let's say I wanted to use the result of this first line and subtract 6 from it. So instead of writing 2 plus 2 minus 6, I can simply just write the result of the first line, x minus 6. So now if I evaluate this cell, I have two different inputs, and I can expect two different outputs. The first output would be 2 plus 2 or 4, and the second output would be 4 minus 2 or 6. So let's go ahead and evaluate it by hitting Shift Enter, and exactly what I expected has resulted. I have a unique input 3, and then have been given two different outputs 3 and 4 because there are two different inputs or two different lines that I'm asking Mathematica to output within my input. So now let's say that we are not interested in this first output, the output of 4, because for whatever reason it's some sort of intermediate calculation and we only want to know the result of the last line. So if you need Mathematica to evaluate a line like this first line but don't want it to report the output of that line, you simply mark the end of that line with a semicolon. So I've done that here. So now if I reevaluate, I will only get one output. So I just hit Shift Enter, and that output is of any line that does not have a semicolon at the end. So before we move on, I want to emphasize something. By evaluating this cell where x is equal to 2 plus 2, Mathematica sets the symbol x to 4 until this program is shut down or until you set x equal to some new value. For example, if I change one of these 2's to a 1 and then reevaluate, now x is equal to 3, so 3 minus 6 is equal to minus 3. Now x is equal to here and everywhere else 3. So everywhere where I type x, it would be equivalent to typing 3. So further, if I open a new notebook and have a cell within that notebook, x will still be equal to 3. If I have a new cell somewhere within this notebook, x will still be equal to 3. And this is true until I shut down the entire Mathematica program. So I'm emphasizing this because it is a source of common error when students are first learning to program in Mathematica. So if you encounter problems, just recall that this is a common issue. There is a way to so-called clear x so that it is no longer designated as a number but is purely a symbol. And I'll go over this method later in topic 6. At this point in the tutorial, I strongly recommend that if you are following along with an open Mathematica notebook on your own computer, that you pause this video and take a few minutes to try some of your own calculations. Remember that learning a new skill like coding Mathematica is generally much more effective if you are experimenting on your own terms as opposed to just following directly on what I'm showing you how to do. So in the next section, I will briefly cover the typesetting tools in Mathematica, which make use of this program to define complicated equations in a more visually appealing way. And in my opinion, using the typesetting features reduces user error. So here we are again in the same notebook that I used to introduce the third topic. So to demonstrate some of the common and useful typesetting features of Mathematica, I'm going to revisit and manipulate the final 2-line cell code that we have written here. So in the previous example, we performed a fairly straightforward calculation in this first line, x equals 2 plus 1. But say we wanted to replace this with something else. Say we didn't want x to be equal to 3, but rather we wanted it to be equal to the sum of two fractions, say 5/8 plus 7/256. So to input that, your intuition might tell you just to use the backslash key to represent a fraction. And that will certainly work within Mathematica. So to demonstrate that, I will place my cursor here immediately in front of the 2, push the backspace button, and then enter 5/8 as a fraction. So I type in 5, then the backslash button, and then 8. And then I wanted to replace this 1 with 7/256. So I will hold down my shift button, push left on my keyboard to highlight the 1, the backspace button, and then again 7/256. So if I execute this cell, or I evaluate this cell, I will go ahead and get the fraction negative 1369 over 256, which is the most reduced form of the result of x, as we have redefined it, minus 6. Now keep in mind that this might be a little difficult to work with. You might want say a decimal number instead of this most reduced fractional form. And I will go over how to do that in topic 6, built-in functions. Now say instead of writing this first term here, 5/8, as 5/8, you wanted to write it in a way that is more visually intuitive. Say in a way that you might write it on a piece of paper. If I were to write 5/8 on a piece of paper, I wouldn't write 5/8. I would write 5 and then a vertical line and then an 8 beneath it in a well-defined numerator-denominator sense. So Mathematica can do that as well. So I'll start by just taking this 5/8 and deleting it. And now to put it in a fractional form, I'm going to use what's called the Basic Math Assistant palette. So I can open that by choosing Palettes and then Basic Math Assistant palette. And here is my Basic Math Assistant. There are 4 areas, the third of which is typesetting. I'll click on that to expand it. And what I can see here is that this button here represents fraction. So I place my cursor where I want my 5/8, choose fraction. The numerator is automatically highlighted, so I'll type in 5, and then to highlight the denominator, I will push the down button on my keyboard and then push 8. So here we are, 5/8 written in a way that you might write it on a piece of paper. So I'll do the same thing here with 7/256. I'll highlight it, delete it. Only this time, instead of starting by hitting this button, I will type in 7, and then I will highlight 7 using my keyboard, and then I will push the button. Now, if I choose the button now, what is highlighted will automatically be placed in the numerator, and the denominator will be highlighted. So all I have to do is push in 2, 5, 6, or 2, 5, 6. And here we go, in a more, I would say, visually appealing form. Now, I'll just evaluate this through Shift-Enter to show that we get the same result, negative 1369 over 256, and we do. So, there's one other way that I want to demonstrate how one can input this 5/8. So, I'll start by highlighting the entire 5/8 and deleting it, and that's with the shortcut key. So if you want to know what the shortcut through the keyboard is for this fraction, you can see here it's listed as Control/. So I'll start by hitting 5, highlighting 5, and then Control/ on my keyboard, and the denominator 8. So I would say that's a little easier way to write it because it's a keyboard shortcut as opposed to having to grab your mouse and go back and forth between the basic math assistant. So again, this evaluates to negative 1369 or 256, over 256. So another typesetting tool that's commonly used within Mathematica is the power typesetting. So let's say instead of wanting to subtract 6 from x, as we do currently in the second line, we wanted to subtract 6 from x squared. So your intuition, perhaps from using Microsoft Excel, might tell you that the way to input this is to place your cursor here and then put the caret key in, which is Shift 6, and then a 2. And this collectively represents x squared. And it certainly does also within Mathematica represent x squared. So if I evaluate this by holding Shift and pushing Enter, I get the most reduced fractional form of the result, which is negative 365,327 over 65,536. Again, I'll teach you how to turn this into a decimal later. But for now, we'll just leave it in its most reduced fractional form. But certainly, if you were writing x squared on a piece of paper, this is not how you would do it. So I'm going to do this in a more visually appealing way by finding within my typesetting basic math assistant the superscript key or superscript button. So I'll push that. The base is automatically highlighted, so I'll type in x, and then I'll use my cursor to highlight the power and type in 2. So here we go, x squared minus 6. So now I'll show you the keyboard shortcut for that, which is listed right here if I hover, which is Control plus 6, or Control plus the key that has the caret on it. So I'll start by typing x, highlight x, Control 6, and then it automatically has the power highlighted, so I'll type in 2. And just to demonstrate that this gives us the same result, I will evaluate this cell by holding Shift and pushing Enter, and we get the same thing. So I've shown you two of the most commonly used typesetting features of Mathematica that make using it a little more visually straightforward. And as you can imagine, there are other typesetting features that you might find useful. And an examination of the basic Math Assistant typesetting palette will certainly give you a sense for what is available. Now, I want to end this topic by demonstrating how one can use the basic Math Assistant to input Greek letters, which are often used as symbols within the physical sciences. So instead of this tab, I'm going to choose the second tab, the Symbols and Greek Letters tab. So to demonstrate use of this, I'm going to turn this 2-line input cell into a 3-line input cell by clicking here and then pushing the Enter key, which now gives us a second line in between what was previously 2 lines. So let's say in the second line I wanted to write define a new symbol, alpha, which is a Greek letter. So I want alpha to be equal to pi minus 1. So to type that in, I find alpha over here, type equals, and then pi over here, and then minus 1. And then because I don't want the result of this line to be an output, I will just put the semicolon at the end of the line. So one thing that I want to point out here in the second line is that alpha is blue. Alpha is highlighted as blue because it represents a symbol that has not yet been defined. Pi, on the other hand, although it's a symbol, is not blue, and that is because it's already been defined by Mathematica. Mathematica defines pi as the ratio of a circle's circumference to its diameter, 3.1415, etc. So we do not have the option as a user to redefine pi. It's already been defined, but we can redefine alpha as we have done here in the second line. So now to actually use this alpha that I've computed in the second line, I'm going to add some form of alpha to the third line, which is my output, because it does not have a semicolon at the end. So let's say I want to have x squared minus 6 plus the square root of alpha. So one way to write that might be to write plus, and then I want to write alpha. So I could just write alpha by, in my basic math assistant, typing or choosing the alpha button. I'll show you the shortcut here, which we see for alpha is escape, lowercase a, escape. So on my keyboard, I'll write escape, and then lowercase a, and then escape, and then my, which automatically is converted to alpha. Now I want the square root of alpha. So I could write caret 0.5, and this would give me my desired result, but I'm not going to do that. Again, the theme of this topic is to make this more visually appealing, so I will highlight alpha and then find the radical button within the typesetting section of the Basic Math Assistant and type that. Now keep in mind that instead of actually choosing this radical button, if I knew the keyboard shortcut was Control and then the key 2, I could have used that instead. So here we are again. In a way, we have 3-line code that is written in a way that is visually intuitive, and that is the same way that you would write it if you were writing it on a piece of paper. So now to evaluate this cell, I will hold down Shift and push Enter, and what I get is somewhat of a mess. So I have what I had before, and then plus the square root of -1 plus pi. So keep in mind again that this is the most reduced form of this output without converting any of these symbols or rational numbers to irrational numbers. I'll explain how to give a decimal result of this later. So in summary, this topic covered how to use both the Basic Math Assistant palette and or shortcut keys to make Mathematica inputs appear in a manner that is more consistent with how most people would write it on a piece of paper. This practice, in my opinion, helps users reduce errors. So in the next section, I'll give an example of how Mathematica can be used as a glorified calculator, or in other words, as a tool to make sure that you are not making errors when plugging numbers into equations that contain a relatively large number of terms. In this topic, I will demonstrate one of the ways that first-time users of Mathematica often find this program to be particularly beneficial. So say you wanted to use the energy version of Coulomb's law to calculate the energy of a system consisting of two charges separated by a constant distance within a vacuum. To do this, one first needs to either recall or look up the correct equation for this version of Coulomb's law. Either from physics or from Wikipedia or from your memory, you can determine that the correct form of the electrostatic potential energy for a two-charge system is that energy is equal to the first charge multiplied by the second charge divided by 4 pi times the permittivity times the separation distance. Know that if we want energy in joules, we must use coulombs for charge, meters for distance, and permittivity of farads per meter. To place this equation into Mathematica, I will start by creating a new Wolfram language cell by just clicking down here and then hitting the Enter button on my keyboard. So now I will type in the equation. So in the numerator, we have the first charge multiplied by the second charge. To conform to commonly used symbols, I will designate the first charge as Q1, so I'll type in Q and then 1. And then multiplied by, I will hit Shift 8 for the asterisk, and then Q2 for the second charge. So here we have the numerator. So to put this in a form that is more visually appealing to write the denominator, I will just highlight the numerator and then go to my Basic Math Assistant palette and choose here the fraction key. And then in the denominator, we have 4 multiplied by pi, so I'll use the short key for that, which is escape, lowercase p, lowercase I, escape, times permittivity of vacuum. So for permittivity, I'll use the Greek letter epsilon, which is escape, e, escape. And then because it's vacuum, I'll type the number 0, epsilon naught, and then times the separation distance, and for which I'll use r. So here's my equation, or at least the right-hand side of the equation. For the left-hand side, I'll just place the cursor on the left-hand side, and we know that this is equal to electrostatic potential energy. So for potential energy, I'll just use the symbol U and say U is equal to this. And then to suppress any sort of output, I will just go ahead and put a semicolon at the end of this equation. So here's my entire equation. So energy is equal to the first charge times the second charge divided by 4 pi permittivity of vacuum times the separation distance. So note that someone might have been, or you may have been tempted to, instead of using U for electrostatic potential energy, you might have been tempted to use E for potential energy. But in just as Mathematica restricts the use of the symbol pi and users defining or changing the value of pi, Mathematica also restricts the use of E. So you can't use the symbol, or you can't redefine the symbol E. So essentially, to make any meaningful calculation from this equation, one needs to know 4 values. So you need to know the first charge, the second charge, vacuum permittivity, and the separation distance. So what is convenient about Mathematica in comparison to using, say, like a calculator to make this calculation, is that Mathematica allows you to write the final form of the equation, as we have done here, and then somewhere else define all of the terms involved in the equation. We've just identified 4 of them. So we can identify those terms above the equation and then make the calculation that we are interested in. So you might be thinking, well, I can do the same thing, which is defining values elsewhere and then using Microsoft Excel to call upon those cells to make a calculation, and you're absolutely right that you can do that. However, I still think Mathematica is beneficial because, unlike in Excel, you can use the typesetting tool to make this look visually appealing, or the way that you would write it on a piece of paper, as opposed to using many nested brackets like you would have to do in Excel. So let's define each of these 4 terms needed to complete the calculation. So I'll start by placing my cursor above the equation and then hitting enter several times to give myself space to define each of these terms. So we'll start with the first term, which is the first charge. So I'll type in Q1, and that is equal to, so this is again the charge, the first charge in the system of 2 charges. So let's make a calculation on a system that is relevant. So let's say a hydrogen atom, where the 2 charges are the charge of an electron and the charge of a proton, that are separated by a separation distance of a hydrogen Bohr radius. So essentially we're calculating the electrostatic potential of a hydrogen atom. So the first charge is then the charge of an electron in coulombs. So that charge is negative 1.602 times 10 to the negative 19 coulombs. So I've entered the 1.602 part. Now I'm going to enter times 10 to the negative 19th. To do that, I will say times and then 10. Highlight this and use my power button in typesetting, and then minus 19, and then end it with a semicolon. Because again, I'm just defining this term. I'm not interested in knowing the output of this. So now I will type in the charge of the other point charge in this case, which is the proton, which, as you remember from general chemistry, electrons and protons have equal and opposite charges. So this is the same thing, just with the opposite sign. So 1.602. Only now, instead of writing times 10 to the minus 19th in this way, I'm going to show you Mathematica shorthand for times 10 to the power. So that shorthand is the multiplication sign times, and then if immediately after the multiplication sign you hit Shift 6 and put a caret in, then this Mathematica interprets this as times 10 to the, and then I'll type negative 19. So functionally, Mathematica will interpret this portion and this portion as the exact same thing. So it's useful to point out now that there is a faster way that I could have defined our second charge, Q2. I could have just written Q2 equals negative Q1, since I've defined Q1 in the above line. Here I would just be defining Q2 as the opposite, or the opposite sign of Q1. That would have used fewer keystrokes, and I certainly could have done that, but for the purpose of a demonstration, I'll just do it the long way. So on the next line down, I'll define vacuum permittivity, which is epsilon naught. So escape lets me write epsilon, 0 lets me write epsilon naught, and this vacuum permittivity in farads per meter is 8.85 times 10 to the negative 12. So I'll do asterisk, caret, negative 12. 8.85 times 10 to the negative 12. And then a semicolon at the end. And on the final line, I'll write the separation distance between the two charges, which is r. So I'm going to use the hydrogen atom Bohr radius, which is 5.29 times 10 to the negative 11th. Okay, here. Okay, so 5.29 times 10 to the negative 11th. So, so here I've defined each of the four terms that we need to define to be able to calculate the electrostatic potential energy of this system. So now I'll put my cursor here and just kind of get rid of some of these extra spaces for neatness. I want to point out now that there are 5 total lines in this code, and each line ends with a semicolon. So if I executed this code now, it would define Q1, Q2, epsilon naught, R, and U. However, it wouldn't output anything, which is kind of a problem, because that's what we're interested in doing, is making an actual calculation and knowing what the result of that calculation is. So what I will do is just have my cursor here and then push enter, create a 6th line, and then type in U, which will print out or provide in an output the result of U. So essentially the first 5 lines, I'm defining things, I'm making calculations based on those based on the definition of those terms, and then finally I'm outputting what I'm actually interested in. Okay, so now let's go ahead and perform this calculation. I will do that through Shift Enter on my keyboard, and here is our result, negative 4.362 times 10 to the minus 18 joules. Now, how do I know this is joules? Well, I know this is joules because I used the correct units as I described earlier. Now, note that this output looks significantly different than this output. This is almost all symbols here, where this is actually a number. This is a number because we already limited the precision of the output by typing in irrational numbers here. So it gives an output of an irrational number. So one thing that I want to show you before moving on is adding comments to this essentially 6-line program. So oftentimes people who write code, they will place comments within that code to identify variables or make notes of logic or strategy while they were making that code. And this practice can be extremely useful if you plan on writing some code that you think you might need to use at a later date after not using it for a while, or if you're writing code that you think might be used or interpreted by someone else. So for example, if you open this notebook a year from now after not having seen it, you might be confused as to what U is or what Q1 or epsilon naught is. So comments are just written characters that the program, in this case Mathematica, skips over when evaluating a cell. So I might want to write here that Q1 is the charge of an electron in coulombs. So to do that, I'm going to add a comment. I'll just put a few spaces after the definition of Q1, and then to define my comment, I will write open parentheses, asterisk, and then a few spaces, and then asterisk and close parentheses. So essentially, what I've done here is provided some space that will not be evaluated when I evaluate this cell. Mathematica will basically just skip over what's inside of this designated area. So I will write my comment here, which is charge of an electron in coulombs. So later, if I open this program, I can look at this and say, oh, okay, now I remember what I was doing or what the purpose of this calculation was. So I'll go ahead and highlight all of this, right click and copy it. I could have also used Control-C as a shortcut in Mathematica, and I will paste that here and here. Here I'm pasting just by hitting Control-V. I could also right click and choose paste. So I will provide a comment after each one of these first 5 lines for someone else or for myself to be reminded about the purpose of this program. So this is the charge of a proton. This is vacuum permittivity in farads per meter. This is point charge separation distance in meters. And finally, this is electrostatic potential energy in joules. And just to prove that the addition of these comments doesn't change in any way the way that this code is actually interpreted and ran by Mathematica, I'll evaluate the cell again by placing my cursor here and hitting Shift-Enter, and we get the same result as we had before. So note here that, again, this is just a number. And because I know what all of the units are, this number is, I know that the unit of this resultant number is joules. So I'm emphasizing this because it is always a good idea to perform a dimensional analysis or a calculation and a combination of units when performing calculations of this manner. So for example, if I would have used Bohr radius here in angstroms instead of meters, it would have given a hugely different number here, and then the unit would no longer be joules. So just so that the calculations you perform are correct and you know what they are, always do a dimensional analysis. So at this point, I'm again going to strongly recommend that if you are following along with an open Mathematica notebook, that you pause this video and take a few minutes to try some calculations on your own. Using Mathematica as a glorified calculator in this manner can be a nice way to organize calculations that are more complicated than what is typically quickly punched into a handheld calculator. So in the next section, I will briefly highlight some of the built-in functions within Mathematica that make calculations easier. The second to last topic of the tutorial covers some of the functions that are built into Mathematica. To start, let's state explicitly what a function is within Mathematica. So upon first hearing it, the word function might invoke thoughts or memories of f of x, or f is a function of the variable x. In this case, a function is simply some relationship that has a variable and you choose to input a value for that variable so that the function outputs a value. So in a sense, it's a type of input-output relationship similar to what we did, say, in this first cell. To demonstrate one of the built-in functions of Mathematica, I will open a new cell by clicking here and hitting the Enter key. I'm going to use the trigonometric function of sine, which for a given angle within a right triangle is the ratio of the side opposite to that angle to the length of the longest side. Most calculators have the sine function built in, and it's likely that you have learned how to use it, for example, to determine that the sine of pi over 2 radians is equal to 1. Remember that pi over 2 radians is equal to 90 degrees, so in other words, the sine of 90 degrees is equal to 1. So to use sine within Mathematica to make a computation, we simply type the function in that corresponds to trigonometric sine, which I know from memory is capital S-I-N. So I'll go ahead and type capital S-I-N in. We now need to input a value for the variable of the sine function, which is an angle. So oftentimes variables for functions are written on a piece of paper as surrounded by parentheses. But it's important to know that in Mathematica, the variables or inputs for any function, including the sine function, are always surrounded by brackets, not parentheses. The sine function in Mathematica only has one input, which is the angle. So I'll go ahead and write open bracket, closed bracket. By default, Mathematica assumes that all angles input into the sine function are in radians. So I will input the angle pi over 2 radians using the typesetting shortcut of Control / for fraction. So I'll place my cursor within the brackets to input the variable, and then I'll type in pi over 2 by using the shortcut key for pi, so escape, pi, escape, highlighting pi, hitting Control / for the fraction shortcut, and then typing 2 on my keyboard. In similar fashion as to the previous topic, I will make this line equal to some symbol. So I'll just make that symbol y equals, and then at the end of this line I will place a semicolon. So it might be a little strange that I have this line, but I don't want it to actually be output, and now on a second line I will put that symbol as an output. This might seem a little superfluous, a little unnecessary, but later hopefully this will be a little more obvious why I'm doing this. So to evaluate this cell, or to compute sine pi over 2, place it in the variable y, and then output the variable y, I will hit Control Shift Enter. I'll go ahead and do that now, and we get the result that we expected to get, which is that the sine of pi over 2 radians is equal to 1. Now, let's say I wanted to calculate the sine of something that was a little bit more obscure, say pi divided by, instead of 2, 123. So I'll go ahead and type in 123 instead of 2. If I evaluate this cell, I get a result that perhaps is not useful, which is basically telling me that the sine of pi over 123 is in fact sine of pi over 123. This is because when Mathematica is faced with turning a rational number, such as the sine of pi over 123, into an irrational number, such as a number with a certain number of places after the decimal, it would necessarily be losing precision because of its report of a finite number of decimal places. Instead, the most exact rational form of the input of sine of pi over 123 is just that. It's the sine of pi over 123. Contrast this with the sine of pi over 2, which we computed earlier, which is an exact rational number, 1, with an infinite number of zeros after the decimal. So we're not losing any precision by reporting that as 1. However, here I might want to know what the sine of pi over 123 evaluates to in numeric form. So to do this, I will use another built-in function in Mathematica, and that function is the n function, which converts any symbolic result, such as the sine of pi over 123, to a numerical truncated decimal result. to use this function, I will add a third line to the cell and write capital N, which is the numeric evaluation function, followed by an open and a closed bracket. The input of the N function, which is an expression that I would like to evaluate numerically, is y. So I will place y inside the brackets here. Now if I evaluate this cell, and I'll do that by hitting Shift Enter, I get two outputs. The first is the output of y, which I didn't ask Mathematica to evaluate numerically, so it's sine of pi over 123. And the second is the numeric form, which is 0.0255386. Realize that the N function, as I used it here, only has one input or one argument. In Mathematica, the values that you input inside of the brackets or into the function is called an argument. That one argument in this N function is the number that you would like to analyze numerically. I also want to point out that the N function can be used with two arguments, which I will do below on a fourth line of code. So I'll hit Enter to create that fourth line, and I will start by writing the N function itself, and then open and closed brackets again. Now, to divide the two arguments within the variables of the function, or the inputs of the function, I will go ahead and click here and add a comma. Note that whenever functions in Mathematica require more than one argument or have an option to input more than one argument, those arguments are separated by commas. So to the left of the comma, I'll place my cursor there, I'm going to place the rational number that I would like to be evaluated numerically, which is y. To the right of the comma, I will put a whole number that indicates how many digits of precision I would like the number to be reported. So let's go ahead and write 10. Now when I evaluate this cell, the output is reported only similarly as it was before, only with more digits of precision. So 0.02553862673, which is a total of 10 digits of precision. So as an additional example, I will create another line of code, and here I will say I want to see what the value of the irrational number pi is to 200 digits. So I'll type that in very quickly. So I want n, and then I want to evaluate pi, escape, pi, escape, and then comma to, I said 200 digits of precision, and then n bracket. Now if I evaluate this, I get the same three results that I had before, plus a fourth result, which is 200 digits of precision of pi. I don't know how useful this is, but it's kind of a neat example. So finally, I would like to return to something that I mentioned earlier in topic 3, in which we last defined x as 5/8 plus 7/256 up here. Just to demonstrate that the symbolic assignment performed earlier in this notebook still holds, I will begin a new cell by clicking down here and hitting Enter. I will simply type x and evaluate it. So x and Shift Enter. And as I said, x is still equal to 167 over 256. Just to demonstrate how this rational number can be instead expressed as an irrational decimal with, say, 10 digits of precision, I will type in a new line of this cell and use the n function on x with by requesting that I get 10 digits of precision. So I'm going to type in n, open bracket, x, comma, 10, close bracket. And now when I hit Shift Enter to evaluate this cell, I can see that, as I mentioned previously, I get two outputs. And the first is a rational number, and the second is an irrational number with 10 digits of precision. So as I said before, there is a way to evaluate these fractions or these rational numbers, which can sometimes be awkward to work with, into irrational numbers that we're more used to working with, like decimals. It just involves using the built-in n function. Moving on, I want to point out how the assignment of a numerical value to x can be problematic. This can be a problem if, say, you wanted to use x as an open, unassigned symbol, or in other words, a variable. To demonstrate, I will start a new cell by clicking below this line and hitting Enter. In this cell, I will introduce another built-in function, the solve function. This function requires 2 arguments and can be used to solve for the value of an unknown. To use solve, I will type in the name of the function, which is solve with a capital S, and then open and closed brackets. As I said, this function requires 2 arguments, so I will place a comma within the brackets to separate the arguments. The first argument is a mathematical equality. So to the left of the comma, I will type in that 2 is equal to x squared, x squared minus 7. So I type in 2, then equals, and then another equals sign. So note that when you're typing in an equality within the solve function, you need to use double equals. And then x squared using my shortcut of Control caret, and then a minus, and then 7. There, that is my relationship for the first argument. Then I want to solve for x, so I need to specify that, which is done in the second argument. So to the right of the comma, I just type in x. So again, the solve function is used if I have a mathematical relationship, such as this one on the left, and I want Mathematica to solve for an unknown, which here is x, that makes this relationship on the left true. Now, if I go to evaluate this, and I'll do it right now by hitting Shift-Enter, I get an error. And what this error says is that 167 over 256 is not a valid variable. This is happening because the symbol x, as I tried to use here, is not cleared. Or rather, it is associated with the value of 167 over 256. So the built-in solve function cannot use it to arbitrarily solve for this relationship. So one thing that I could do is simply choose another variable. Now I couldn't choose y because that is used up here, but I could choose, for example, z. So if I replace these two x's with z's here, this first one and this second one, this error would not happen and the solve function would work properly. However, I want to instead demonstrate another built-in function, and that built-in function is called clear. So above the line in which I wrote solve, I'm going to type in clear with a capital C, C-L-E-A-R, and then open and closed brackets. What the clear function does is it takes away any numerical assignment to a symbol. Note that if the clear function, if you want it to, it can contain as many arguments as you like, all separated by commas. And what it does is clears the symbol assignment for each argument that you input. So, for example, if I wanted to clear both x and y, I would place my cursor inside the brackets and type in x, comma, y. But for now, I think I'll just clear x. So I'll type in x. So if I evaluate this cell now, what it's going to do is clear x, get rid of its numerical assignment of 167 over 256, before x is used as an uncleared variable within solve. So hitting Shift-Enter now does not result in an error. Instead, it gives the two possible values of x that make this relationship here true, which are 3 and -3. So in summary, I have taught you a few built-in functions within Mathematica, such as the sign function, the end function, the clear function, and the solve function. So if you like, now would be a good time to pause the video again and try using or modifying some of the code that we've used here so that you can increase your own comfort and familiarity with the use of these functions and generally the use of Mathematica. So in our next and final section, I will answer what may be a lingering question for you. And that question might be, how do you know all of these functions? Did you have to take a class or read a book about Mathematica? And the answer to that question is no, that the vast majority of my personal knowledge of Mathematica has come from either practice or reading the online help section, and usually a combination of those two. I will show you where, for example, you can find a tutorial that teaches you how to define your own functions within Mathematica, as well as find helpful descriptions of some other built-in functions that I did not go over within this section. The final topic of this tutorial will not be a demonstration within a Mathematica notebook or even within Mathematica itself, but rather within a web browser. Here I will show you what a powerful resource the online Mathematica help can be. So in the previous section I demonstrated the use of the sine function. Say you wanted to learn more about this function and see some examples of how it can be used within Mathematica. So to do this, I recommend simply just typing in Mathematica sine function into Google. This first page, the Wolfram documentation page, is what we are looking for. So I click it, and it will navigate me to a page that details the sine function for use within Mathematica. So the top tells me briefly what the sine function does. The details tab here provides some additional information relating to the definition of the function. The background and context tab kind of provides a mathematical basis for the sine function. But in my opinion, besides perhaps this basic definition, the most useful part of this web page are the basic examples given by Mathematica, or by Wolfram for use within Mathematica. So note this is often useful if you are trying out or troubleshooting a function and you're not sure exactly what's going wrong. You can just take this input, copy it, and put it directly into your Mathematica notebook, and then you can kind of tweak it from there. So here we have an example of sine of pi over 3, kind of similarly as to what we used in topic 6. Here's an example of how the sine function can be used with degrees instead of radians. And here's a nice example of how the sine function can be combined with another function, plot, which we'll go over later in this section to give a plot of the sine function. Okay, let's look at another function. So I'll scroll to the top, and here within the search, just type in n and then enter. And this brings me to the n function, which we used a lot in topic 6. So here it tells us that we can use n either with one argument or with two arguments separated by this comma, and gives brief introductions of how n can be used, and then again some examples. Now let's look at a function that we haven't used yet, but is quite common when trying to visualize expressions or data, and that is the plot function. So I'll scroll up and simply type in plot to this search bar, and it will show me the page demonstrating how to use the plot function. Note also that if I didn't know the plot function existed, a well-worded Google search is also quite helpful. So to demonstrate, I'll just open a new tab in my browser right here and type in, how do I make a graph in Mathematica? So I would say this is a well-worded Google search. So as soon as I do this, I get a lot of really useful options. So this second option here, plot Wolfram language documentation, is exactly this page right here. The first tells us generally all of the different plots that can be made in Mathematica, not just using the plot function, all of the different graphs. A kind of a reference or a tutorial about how to create plots, and then also some YouTube videos which directly demonstrate how to use the plot function. So again, a well-worded Google search is quite nice. And this is kind of the take-home message of this final topic within this tutorial, that Mathematica is widely used software, and it has solutions or solutions to many common problems or guides to achieve many common tasks encountered when using Mathematica are easily accessible online. So use the resources that are available to you, especially those that come from a straightforward Google search as this. So I'll just jump back to this page that discusses the plot function. Note here that there are 4 different ways to use the function, and each way requires 2 different arguments. For example, the first way is that the first argument is the function you're wishing to plot, and the second argument contains three subparts. The first subpart of the second argument is the variable that you're plotting over, so the x-axis, and then the minimum and maximum of that variable over which you would like to plot. So I just wanted to point this out because upon first examination, a lot of people might look at this and say, well, there's four different arguments within the plot function, when in fact there are two. The first is just a function, and then the second has three sub-arguments that are within curly brackets. One of the options for plotting that I like for my students to use is called the axis label option, and I can see this by scrolling down through all of these examples and choosing options. And within options is axis label. So here are two examples, and in the second example this shows how one can label the x here and the y here axes in a customizable way. So note that labeling of the axes of a plot is important in the same way that providing units with a numerical answer is also important, because it demonstrates that you understand what you are analyzing and what you're presenting to other people. So finally, I mentioned in the previous section that when using Mathematica, one is not limited to the predefined functions shown here, for example, plot. One can actually learn to write their own function. To show this, I will go back to the top and perform a search for defining functions. What I'm looking for here is this third page Wolfram language tutorial of defining functions. Here, this tutorial explains how one can define their own functions of one or more variables. So learning to write your own functions can be quite helpful when making plots within Mathematica, and is generally a useful practice when trying to write clean code. So I would recommend going through this tutorial and trying to educate yourself how to write your own functions. So to end this topic, I would like to again just emphasize that Mathematica is a powerful and widely used piece of software, and that if you are encountering some sort of problem while using it or trying something new, the odds that someone else has encountered that same problem or tried that same new thing and written about it somewhere online are quite high. So the take-home message is to use the Wolfram Documentation Mathematica help, which I have open right here, as well as a well-worded Google search to your advantage. Further, do not hesitate to use your student peers as a resource if you encounter trouble, and as always, your instructor's office hours are there for a reason, and a great resource to help you overcome problems when using Mathematica. Just always remember that if you plan on coming to your instructor's office hours for Mathematica help, it's generally a good idea to first email your instructor the notebook that you are having trouble with, so that your instructor can see exactly what you're doing. I would like to conclude this tutorial by thanking you for watching, and also thanking the University of Colorado, Colorado Springs, the UCCS College of Letters, Arts, and Sciences, and the UCCS Department of Chemistry and Biochemistry, without all of which this video would not have been possible. Thank you for your time and your attention.